Good morning, class, and welcome to Chapter 9. Today we're going to be talking about solutions. As always, please make sure you have a periodic table, pen or pencil, scratch paper, the pre-printed notes, and a calculator to work out the problems. So what is a solution? Solutions are homogeneous mixtures of two or more substances. They are formed when there's enough attraction between the solute and the solvent molecules. Well, what is solute and solvent? Well, a solution has two components, the solvent, which is typically present in the larger amount, and the solute, which is generally present in a smaller amount. Solutions do not have to be liquid. Okay, solutes may be a liquid, gas, or solid. They are spread evenly throughout the solution. They mix with solvents so the solute and solvent have the same physical state. They cannot be separated by filtration, but can be separated by evaporation. A great example of this is if you mix salt and water. You can run salt water through a filter and separate nothing, but you can take the same beaker of salt water, leave it to sit for several days, and at the end you'll have the salt in the bottom while the water will have evaporated off. Solutes are not visible, but can make the solution colorful. Like if you mix a packet of Kool-Aid in water, right? The water's going to turn a pretty color. So gas solutions, you can have a gas in a gas. A great example of this is the air we breathe. The primary solute is oxygen gas, which is what we need. The solvent, or the gas that is present in the largest amount, is nitrogen gas. You could have a gas mixed into a liquid. For example, pop that we drink has carbon dioxide as the solute. And the solvent, what's present in the largest amount, is the water, which is in a liquid state. Another great example of this is household ammonia that you may use for cleaning. The primary solute is the ammonia, which is present as a gas, and the ammonia is dissolved in a liquid, which is the water. You can, of course, have a liquid in a liquid, like, for example, vinegar. Vinegar is actually acetic acid, which is a liquid mixed with water. Or you could have a solid in a liquid, for example, salt, right? Mixed into water gives you seawater. The solute is the sodium chloride, and the solvent is the water. And then finally, you can have a solid in a solid, right? You can have a solution that is a solid. And a great example of that is brass, which is a mixture of zinc and copper. The smaller amount is the zinc, which is the solute, and what's present in the largest amount is the copper, which is the solvent. Steel is also another great example of that. Steel is carbon mixed into iron. So again, your solutions can be solids, liquids, or gases. Your solutes can be solids, liquids, or gases. Water is one of the most common solvents ever in nature. And in fact, it's what we're going to use most often in this course. Water is what we call a polar molecule due to polar OH bonds. And polarity just means that you have opposite poles. In this case, we're talking about charge. One end of the water molecule is more negative than the other end. So you have two poles, a negative pole and a positive pole. Water also forms hydrogen bonds, which is really important in a lot of biological compounds. So water is a really, really important solvent. And again, it's the solvent we're going to use most often in this course. Solutions, again, one more time, solutions form when the solute and solvent interactions are large enough to overcome the solute-solute interactions and the solvent-solvent. So what that means is that there is an attraction between your solute particles. Of course, they're attracted to each other, right? That's why they're a solid, because their particles are attracted to each other. And then if you have water as your solvent, the water molecules are attracted to each other. When you mix the two things, a solution only forms if the attractions between the new particles are strong enough that everyone mixes evenly throughout the solution, including the solute and the solvent. Okay? This happens when they are similar in properties. For example, polar solutes tend to dissolve in polar solutions. Non-polar solutes tend to dissolve in non-polar solvents. A great example of this is oil and water. Water, as we just said, is a polar molecule. So water as solvent is polar. Oil, on the other hand, is often nonpolar. So if you try to mix, say, vegetable oil and water, they don't dissolve. They separate out into two separate layers because they're not close enough in properties for them to form a solution. Other examples of this might be iodine or grease. They are just not polar enough to be able to dissolve in water. Okay. Continuing on, we have three types. We have strong electrolytes. These are compounds that dissociate 100% in water. And dissociate is a word that's different than dissolve, right? Dissolve means to take a solid or a gas and to evenly disperse it throughout the solution. Dissociate means for the molecule to break up, for it to actually break into pieces, and it will form ions. You will remember that ions are atoms that have gained or lost electrons to form either a positive or a negative charge. So again, strong electrolytes dissociate in water, producing positive and negative ions. These form solutions that can conduct an electric current strong enough to light a light bulb. We also have weak electrolytes, which dissociate only a little bit in water, meaning if you have 100 molecules of a substance and only 5 of them break up into ions in water, the other 95 stay as molecules, that would constitute a weak electrolyte. So again, they form a solution with only a few ions and mostly molecules that have not been broken up. And then our final and third category is non-electrolytes. Non-electrolytes dissolve in water but do not dissociate, meaning the molecules stay as whole neutral molecules in water. They do not produce ions and cannot conduct an electric current. Our strong electrolytes typically come from ionic compounds, such as sodium chloride, magnesium chloride, sodium nitrate. Our weak electrolytes tend to come from acids like acetic acid or hydrofluoric acid, or, for example, weak bases like ammonia. Non-electrolytes, which do not ionize at all, tend to come from our covalent compounds, like carbon-containing compounds such as methanol or ethanol, sugar like sucrose, urea. So basically, your covalent compounds tend to make your non-electrolytes. An equivalent is the amount of an electrolyte or an ion that provides 1 mole of electrical charge. Doesn't matter whether it's positive or negative. It provides 1 mole of electric charge. In solution, the charge of the positive ions is always balanced by the charge of negative ions. So you may remember that from previous chapters when we started talking about ionic compounds. Remember that when we paired things, for example, if we had a magnesium ions tend to form a charge with a +2. If we were pairing that with a chlorine ion, and the chlorine ion has a charge of -1, remember that they had to balance out. So you had to have 2 chlorines for every 1 magnesium in order to get 2 minuses for every 2 positives. So your formula was MgCl2. This is the same principle here. In order to dissolve in water, you have to have an ionic compound. An ionic compound has to have its charge balanced. So when you dissolve it in water and it provides electrical charge, the positives and negatives are always balanced out. So if you have 2 moles of positive electrical charge, you must also have 2 moles of negative electrical charge. One equivalent is equal to 1,000 milliequivalents. Okay, and this is one of those conversion factors that I asked you to know way back at the beginning of the semester. Remember that I asked you to know milli, centi, and kilo. So this is the same thing, right? 1 equivalent is equal to 1,000 milliequivalents. So for example, if you have a solution that is a mixture of 0.025 moles of sodium chloride and 0.005 moles of KCl, you have 29 milliequivalents of positive charge, 25 from the sodium and 5 from the potassium. The only anion we have present is the chlorine. So therefore there must be 29 milliequivalents of negative charge coming from the chlorine. There's a handy table here that shows the equivalence of electrolytes in clinical intravenous or IV solutions. Anything with a charge of 1 plus, like sodium, potassium, lithium, ammonium, anything with a 1 plus has 1 equivalent in 1 mole. Also, anything with 1 minus, right? Chlorine, fluorine, bromine, right? Anything with 1 minus would also have 1 equivalent in 1 mole. Other negatively charged ions with just 1 minus would be acetate, lactate, which is not an ion I asked you to memorize, dihydrogen phosphate, which is another one that I haven't asked you to memorize, but if you were told that it had a -1 charge, you would know that there would be 1 equivalent in 1 mole. Likewise, something that has a 2 plus charge, like calcium, magnesium, strontium, anything in group 2, right, that has a 2 plus charge would have 2 equivalents in 1 mole. Anything with a 2 minus charge would also have 2 equivalents in 1 mole, right? For example, the carbonate, hydrogen phosphate, 3 plus. Iron forms a charge of 3 plus. Another good example would be chromium. Chromium can form an ion with a 3 plus. Aluminum can form an ion with 3 plus. Anything with a charge of 3 plus would have 3 equivalents in 1 mole. Anything with a charge of 3 minus would have 3 equivalents in 1 mole. Phosphate, citrate, I can't think of any others off the top of my head, but you can kind of see a pattern here. Plus 1, 1 equivalent. Minus 1, 1 equivalent. Plus 2, 2 equivalents. Minus 2, 2 equivalents. So you can tell how many equivalents are in 1 mole by the charge on the ion. Okay, example 1. The laboratory tests for a patient indicate a blood calcium level of 8.8 milliequivalents per liter. How many moles of calcium ion are in a half a liter of blood? So our starting amount is 0.50 liters. We want to know moles of calcium ion. What conversion factors do we know that we can use to get there? Well, the only thing given in the problem is that the test indicated that there are 8.8 milliequivalents for every liter of blood. Well, we don't have a full liter, we have a half a liter. So that says that we can use that as a conversion factor. We can say 8.8 milliequivalents per 1 liter. Okay, so that gets us to milliequivalents, which does not quite yet get us to moles. What other conversion factors do we know that we could use here? How about something that would allow us to go from milliequivalents to equivalents? How many milliequivalents are in an equivalent again? Well, milli indicates that there are 1,000. 1,000 milliequivalents for every 1 equivalent. So we're getting closer, right? We're now at equivalents. We still want to get to moles. Do we know any other conversion factors that would enable us to get from equivalents to moles? Well, from the previous slide, you might remember that you can tell how many equivalents are in a mole by looking at the ion. What kind of an ion is a calcium ion? Well, calcium comes from group 2, and so therefore a calcium ion has a charge of +2. So in 1 mole of calcium ion, we have 2 equivalents. 2 equivalents per mole. So this gets us to moles of calcium. Let's put this into our calculators here. Okay, so we have a half a liter times 8.8 should get us 4.4 milliequivalents. Divide that by 1,000 to get to equivalents. That gets us to 0.0044. And then 1 mole of calcium has 2 equivalents. So if we divide by 2, we should get 0.0022. 0.0022 moles of calcium ion in that half a liter of blood. Okay, let's talk about solubility, which is really important in this chapter. Solubility is the maximum amount of solute that dissolves in a specific amount of solvent. This is temperature sensitive. and is usually expressed as grams of solute in 100 grams of solvent, which is usually water. So again, we typically express this as grams of solute per 100 grams of water. Gout is a disease that primarily affects adult men over the age of 40. Attacks of gout may occur when the concentration of uric acid in blood plasma exceeds its solubility of 7 milligrams per 100 milligrams of plasma at 37 degrees Celsius. So what happens when it exceeds its solubility? Well, if you have more than 7 milligrams per every 100 milliliters of plasma, the excess is turned into a solid because it's no longer dissolved in the plasma. That solid tends to collect in the joints, which is very painful. So that's kind of an explanation of gout using solubility. Unsaturated solutions are solutions that contain less than the maximum amount of solute. And that means that there's still room within the solution to dissolve more solute. So again, if you're unsaturated, you have less than the maximum amount, and there is still room to put more in. Saturated solutions, on the other hand, contain the maximum of solute that can dissolve, which means that there is undissolved solute at the bottom of the container. And it also contains solute that dissolves, as well as solute that is recrystallizing in an equilibrium process, which means if you have a beaker with your liquid in it, and you have some solute dissolved in your solvent, and some of it sitting as a powder on the bottom of the beaker, what happens is some of the solute that is dissolved has a tendency to fall out of the solution and down to the bottom of the container. When that happens, your solution is no longer saturated, and some of the solute that was sitting at the bottom is now dissolved in a cycle that flows. And we call this an equilibrium process. So let's look at an actual example. At 40 degrees Celsius, the solubility of potassium bromide is 80 grams for every 100 grams of water. We want to identify the solutions as either saturated or unsaturated and explain why. Solution A has 60 grams of potassium bromide added to 100 grams of water at 40 degrees Celsius. We were told that you can dissolve up to 80 grams of potassium bromide for every 100 grams of water. So this solution is unsaturated because we could still dissolve theoretically another 20 grams of potassium bromide before we hit our max of 80. So that solution is unsaturated. Let's look at example B. Example B says 200 grams of potassium bromide are added to 200 grams of water at 40 degrees Celsius. Well, for every 100 grams, we can dissolve up to 80 grams of potassium bromide. We have 200 grams of water, so we can dissolve a total of 160 grams of potassium bromide. We have 200 grams. 200 is more than 160. So therefore, our solution is saturated, and we should have about 40 grams of the potassium bromide sitting at the bottom of the container. Okay, saturated. Example C. 25 grams of potassium bromide are added to 50 grams of water at 40 degrees Celsius. In every 100 grams, we could dissolve 80 grams of potassium bromide, which means that for every 50 grams of water, we could only dissolve 40 grams of potassium bromide. We have attempted to dissolve 25 grams. That is less than the maximum amount of 40. So this solution is an unsaturated solution. Okay, so solubility again depends on temperature. The solubility of most solids increases as the temperature increases. So I always tell students it's kind of like if you're dissolving Kool-Aid. Ever notice that if the water is really cold that you're dissolving the Kool-Aid powder in, it's really hard to get it all dissolved? Whereas if the water's warm, it's super easy to get the powder to dissolve. Same thing with laundry. If you ever fill up the laundry tub and you go to pour in the soap, if it's powdered soap, you might notice that if you're doing a load of laundry in cold water, it takes forever to get that stuff to dissolve. Whereas if you're doing it in hot water, it dissolves almost instantly. And so again, the solubility depends on the temperature, and the solubility of most solids increases as the temperature increases. The opposite is true for gases. The solubility of gases decreases as the temperature increases. So let's use this to explain why a bottle of pop could burst if left in the sun. So if we have our bottle of pop here, okay, and I'm a pretty terrible artist here, but we've got our bottle of pop. The level of the pop comes up to just below the level of the top of the can. Now you might remember from the previous page that a solution of pop has carbon dioxide gas dissolved in the liquid, which is mostly water. Now, as the temperature increases, which we would assume it would do if it was left in the sun, as the temperature increases, what happens to the solubility of the carbon dioxide? Well, the carbon dioxide is a gas, so its solubility decreases as the temperature increases. Since carbon dioxide is a gas and not a solid, it does not collect at the bottom of the container. Instead, it rises up out of the solution, right, and into the space between the top of the liquid and the container. As the temperature increases and the solubility decreases, more and more of the gas will leave the liquid and land in the space that's left between the top of the liquid and the top of the can. What happens to that space? Well, it gets more and more crowded with gas molecules, and the gas molecules, as they strike the walls and the top of the container, exert pressure. Remember, that is the definition of pressure. It is the force exerted by the gas molecules on the walls of the container. More gas molecules, more pressure. If the pressure builds up enough, the bottle bursts, particularly in aluminum cans, because aluminum is not a very strong metal, and carved into the top of your aluminum can is a little groove where the tab is that pops in. So that is your weakest area. Leave it in the sun long enough and you can burst your bottle. Example 2, why do fish die if left in water that is too warm? So if we have our little ocean here and we have our little fishies swimming around, we want to know, why can't they survive if the water gets too warm? Well, fish, like you and I, breathe oxygen, right? Only in the case of the fishies, the oxygen gas is dissolved in the water. Fish have little gills, and as they swim through the water runs across their gills and they extract the oxygen gas from the water. If the water gets too warm, the solubility of the oxygen gas decreases and the oxygen gas leaves the water and heads out into the atmosphere. If enough of the oxygen gas leaves the water, then the fish can't get enough oxygen to breathe and they die. So that is why fish die if left in water that's too warm. Henry's law states that the solubility in a gas, in a liquid, is directly related to the pressure of that gas above the liquid. At higher pressures, more gas molecules dissolve in the liquid. At lower pressures, more gas molecules escape the liquid. When we start talking about soluble versus insoluble ionic compounds, only ionic compounds with a soluble ion are soluble in water. Well, what does soluble mean? So soluble means dissolve, right? So if they're soluble, they stay dissolved in the water or the solution. If they're insoluble, they sink to the bottom of the beaker in a solid, which we call a precipitate. So in an insoluble ionic compound, the ionic bonds between the two ions, the positive and negative ion, are too strong for the water molecule to break. So remember we said that the solvent interactions, right? You've got your water molecules over here, and the solute interactions. We said in order for a solution to form, the interactions between these molecules and these molecules had to be weak enough that these interactions could overcome them. So the interaction between the solvent and the solute, this interaction had to be strong enough to break the solute and the solvent. Okay? In an insoluble compound, this isn't true. And instead, they stay solid and they sink to the bottom of the beaker. We have a set of rules that can help tell us whether a compound is soluble or not. And this little handy table here will help us figure this out. So any ion that contains the following: Lithium, sodium, potassium, rubidium, cesium, or ammonium is always soluble. Always, meaning it will stay dissolved in solution. Now, if you look at your periodic table, you might notice something. The first 5 ions all have something in common. Lithium, sodium, potassium, rubidium, and cesium all come from group 1. So group 1 ions are soluble, as is ammonium. If you are a negative ion and you consist of a nitrate or an acetate ion, nitrate or acetate here, you are always soluble. If you are a chlorine, bromine, or iodine, you are usually soluble, except if you're combined with silver, lead, or mercury. If you are a sulfate ion, you are usually soluble except when paired with a barium, a lead, a calcium, a strontium, or a mercury. Now, these are not rules you need to memorize, but you do need to know how to use them. So the next few examples are going to be geared towards teaching you how to use these rules. Okay, so let me tell you how we're going to do this, and then we'll do several examples. We are going to learn how to write an equation for the formation of an insoluble ionic compound. Step 1 is to break everything into ions. If you're not sure where to break something, a really useful hint is to break it at the metal. Step 2, write out the combinations of ions and determine the solubility of any new products. So we're going to write out the ions, see what sorts of new products we could make, and then check the solubility of each of those. Step 3, write the ionic equation, keeping together any solids formed. So we're going to write an ionic equation, which is composed of ions, hence the name, but we are not going to break into ions any solids that are formed. Step 4 says to cancel any spectator ions. Well, what the heck is a spectator ion? We haven't talked about that. In sports, a spectator is someone who is watching the game but not participating. In chemistry, it's pretty much the same thing. A spectator is an ion who's just kind of hanging out, not really doing anything. So for spectator ions, we're looking for ions that are completely, positively unchanged from the left side of the arrow to the right. And then finally, our last step will be to write the net ionic equation. So let's try some examples. We will see that potassium, right, is in the first row here. So potassium is always soluble. So we know that the compound with the potassium in it is going to be soluble and will not form a precipitate. What about the other one, the lead sulfate? Well, sulfate here is soluble most of the time, except when combined with barium, lead, calcium, strontium, or mercury. Since we are paired with lead on the following page, okay, we're going to use the solubility rules to predict whether a solid, which we call a precipitate, whether it forms when we have 2 solutions of 2 different ionic compounds that are mixed. We're going to mix lead 2 nitrate and potassium sulfate. And we want to know whether or not we get a solid and what we get. So our first step was to break everything into ions. Remember our hint to break at the metal. So we're going to break at the Pb here and the K2 there. All right, you may not know off the top of your head what charge is on a lead ion. However, you should know what the charge on a nitrate ion is. That's one of those that I asked you guys to know. It's in the table on D2L. Nitrate always has a -1. So lead, since there are 2 nitrates and each one is a -1, and there's only 1 lead, its charge must be a +2. So again, nitrate has a -1. There are 2 of them for a total of 2 negatives. There is only 1 lead. So in order for this to be neutral, the lead must have a charge of +2. So we have Pb2+ and NO3-. Breaking this other species apart at the potassium, there are 2 potassiums. We know from looking at the periodic table that potassium is always a +1. So there are 2 pluses here, 1 from each potassium. Now, sulfate was on the list, but if you had forgotten it, you could see that sulfate must have a charge of 2 minus, since there is only one of them, and the potassium, each one has a charge of +1. So we have a K plus, and there are 2 of them, and SO4 2 minus. Now, what sorts of new products could we make? Clearly, the lead and the nitrate can pair because they were paired in the original product. So that's not a new product. Can the lead pair with the potassium? Well, lead has a charge of 2 plus, and potassium has a charge of 1 plus. Two positive things do not pair together because they're both positively charged. And just like two North Pole magnets or two South Pole ends of magnets will not come together, two positively charged ions will not pair together. Instead, they repel each other. So we're not going to get lead paired with potassium. However, the SO4, the sulfate ion, has a negative charge, so that lead would be perfectly happy to pair with the SO4. Since the lead has a charge of 2 plus and the SO4 has a charge of 2 minus, they form together in a 1-to-1 ratio. So Pb2 plus SO4 2 minus gives you PbSO4. Now let's look at the potassium. We already know that the potassium and the sulfate can pair since they were paired in the original compound. So that's not a new product. We have ruled out the potassium pairing up with the lead because they're both positively charged. That means that the only other possibility is to pair it with the nitrate. Since the potassium is a +1 and the nitrate is a -1, they will pair in a 1-to-1 ratio, or K plus NO3 minus gives you KNO3. Now, if we go back to the previous page and look at our table, we know that we are going to form an insoluble compound or a solid. So putting this together, we have Pb2 plus SO4 2 minus plus 2 potassiums, each with a positive charge, plus 2 NO3 minuses, gives us PbSO4 solid plus 2K plus 2 NO3 minus. So we have written the ionic equation, however, we keep the solid together. Okay, that was a step on our previous slide. You keep the solid together. Everything else stays in ionic form. Now, we're going to write the net ionic equation by removing the spectators. Again, spectators are anything that shows up unchanged on both sides of the arrow. So Pb plus 2 is not unchanged, right? Instead, it becomes part of PbSO4. The SO4 2 minus is also not unchanged. It's part of the PbSO4 here. Potassium, 2K pluses. There are, on the right side of the arrow, 2K pluses. Those are completely unchanged. So, let's use a different color here. Let's cross those guys out. My 2 NO3 minuses. You've got 2 NO3 minuses here and 2 NO3 minuses here. They are completely unchanged. So let's cross those out. Well, what are we left with? We are left with Pb plus 2 plus SO4 2 minus gives us PbSO4 solid. And that is our net ionic equation. Now, let's try another one. Okay, example 4. What new compounds are formed when hydrochloric acid plus aqueous NaOH, or sodium hydroxide, react together? So hopefully you remember that hydrochloric acid is HCl plus NaOH, right? And we want to determine what new products are formed, what is the total ionic equation, and what is the net ionic equation. Well, in order to determine what new products are formed, we must break these down into ions. The first one, hydrochloric acid, we don't have a metal, but there are only 2 ions possible. Right? There's only 2 elements, so it has to break here. We have H plus and Cl minus. NaOH, right? Again, we break it the metal. Sodium metal has a charge of +1. And that means then that the OH must have a charge of -1. Though you should remember hydroxide from your polyatomic ion chart. Now, what new products can we form? Well, we already know that the hydrogen and the chlorine can pair together since they were initially paired. We hopefully remember from the previous example that two positive things do not want to come together. So the H and the Na probably not going to form a compound. However, the H may be very happy to pair with the OH since they are of opposite charge. So a possible product would be HOH. That looks kind of funny. Don't we normally pair like elements together? How about this? H2, two H's plus an O. Recognize that compound? Oh yeah, that's water. So let's rewrite this. H2O. Other possible products. Well, let's see here. The sodium, we already know it can pair with the OH, so that is not a new product. We've already ruled out the possibility of it bonding with the hydrogen. So the only other possibility for it to bond with is the Cl-. So we could have an Na, which has a +1, and a Cl, which has a -1. So that's a 1-to-1 relationship. Okay, so this equation, when written like this, is called the balanced molecular. Now, clearly it's a little bit messy, so let me change back to black here, and let's write this out one more time. HCl plus NaOH gives H2O plus NaCl. This is called the balanced molecular equation. We want to get the total ionic equation. Remember that to do that, we break down everything into our ions, keeping together the solids. So initially we had H plus Cl minus plus Na plus OH minus. Now on the other side of the arrow we said to keep together the solids. Sodium chloride, do you think that forms a solid or not? If you flip back 2 pages on your notes, you will see that sodium chloride contains a sodium ion, and sodium ions come from group 1. So sodium ions are always soluble, meaning they stay broken up. So we can put these back into ions, Na plus and Cl minus. Now, H2O is not a solid, right? It's water. It's liquid in this case. However, water does not break up into ions in water, right? So we don't have to worry about whether water is soluble in water because water is water. So we're going to leave the water alone, okay? H2O. This is our ionic equation, and this is our ionic equation. To get the net ionic equation, we have to do something, and that is to remove the spectators. Okay, we're going to remove the spectators. Is the H plus completely unchanged between the left side of the arrow and the right? Well, I would say no. You have an H plus here, and here it's part of the water. So we're going to keep the H plus. How about the Cl minus? I have a Cl minus here and a Cl minus here. Those are completely unchanged. So I'm going to call those spectators and get rid of them. How about the Na plus? I have an Na plus here and an Na plus here. I would call those spectators. Boom, boom, gone. The OH minus is not unchanged, right? It's part of the water on the other side. So let's keep that as it is. And then finally, the last thing we have on the right side of the arrow is the water. So again, we have a balanced molecular equation. We have our total ionic equation and our net ionic equation. Let's try another one, because I know that this concept can sometimes be kind of tricky. Example 5. What new compounds are formed when barium chloride, BaCl2, and potassium chromate, K2CR, React together. What is the total ionic equation and what is the net ionic equation? So let's start by breaking everything down into ions to see what sort of things we could form. We have a barium, which forms a +2 based on its location on the periodic table. And we have two chlorines, which form a -1 based on their location on the periodic table. For the second molecule, it's not as easy to see where to break, right? Because we have more than two things, but we're going to break at the metal. So we're going to have two potassium ions. Each one's a +1. If each one of those is a +1 and there's two of them, what does the charge on the chromate have to be? This is not one of the ones you were asked to memorize. However, you can determine the charge on it by looking at the potassium. Since there are two pluses from the potassiums, this must be a 2-. Now, possible products. We know that the barium and the chlorine can pair together since they were paired in the original molecule. The barium and the potassium are unlikely to pair together because they're both positively charged. The barium and the chromate have opposite charges, and they are not on the left side of the arrow, so that could be one of our new products. Since the barium is a +2 and the chromate is a -2, they pair in a 1-to-1 relationship. BaCrO4. Okay, now let's look at the potassium. We already know it can pair with the chromate since it was paired with it originally. We've already determined that it could not pair with the barium since they're both positively charged, so that leaves it to pair with the chlorine. We have two potassiums and two chlorines, each with a +1, -1. So that means that we would have two potassium chlorides, one potassium, one chlorine, and then two of them, one for each of these two. So our balanced equation contains one barium on the left, one barium on the right, two chlorines on the left, two chlorines on the right, two potassiums on the left, two potassiums on the right, one chromate on the left, one chromate on the right. So this is our balanced equation, balanced molecular equation. How do we get from here to the total ionic equation? Anybody remember? What do we have to do? Okay, well, what we have to do is we have to determine if any of our two new products are solids, and then we're going to go back and write everything as ions except for whatever was a solid. So if you remember from that table, anything in group 1 is always soluble, meaning it dissolves, so it's not a solid. Potassium is in group 1, so we don't have to worry about that forming a solid. That is going to break up. So in our ionic equation, we have the Ba2 plus the 2Cl minus plus the 2K plus the CrO4 2 minus. Now, on the right side of the arrow, we have 2K pluses and 2 Cl minuses. Now, I'm going to have to come down here on the next line because I'm running out of space. Let's look at the barium chromate. Now, the short list of rules that you were given within the notes does not cover that situation. There is no chromate ion. However, if you look at the expanded solubility rules found in D2L, you will see that the barium chromate is insoluble. Insoluble, meaning it forms a solid. So we're going to keep that together. BaCrO4. Now, to get our net ionic equation, we have to do something. We have to cancel the spectators. Is the barium 2 plus a spectator? I think not. It has been changed. If you look at the right-hand side of the arrow, it turns into BaCrO4. So let's keep our Ba plus 2. How about my 2 Cl minuses? They look pretty unchanged to me. I have 2 here and 2 here, and they are no different. So they go away. Bye-bye. How about my 2K pluses? Again, boom, boom, gone. They did not change at all. They're spectators. My CrO4 2 minus, it looks like it is turning into BaCrO4. So it is not a spectator. And the only thing left on the right-hand side is BaCrO4. So, balanced molecular, total ionic, net ionic. So this concludes Chapter 9, Part 1. There are 2 more parts to this chapter, so I hope to see you back for Chapter 9, Part 2. Have a great day.